We're going to complete this example where we find all of the eigenvectors for this matrix C. Our first step is to compute C minus lambda I, where lambda here is equal to -1. So C minus -1 times I. This is going to be the same thing as calculating C plus I. Okay. So for us, this looks like 2, -2, -2, 2. Again, notice this isn't invertible. That's a good thing. That's what we're looking for. I'm trying to find all solutions to this equation C plus I times V is equal to 0. My solutions are going to be my eigenvectors. So the augment of 0 is kind of nice because it reminds us of where this is coming from, but it's not really necessary, so I'm going to leave it off this time. So I'm going to row reduce for a second. I'll let you do that. Okay, and what we find is that we have solutions. If this is x and this is y, my solutions are x minus y is equal to 0. So x and y have to be equal. So my eigenvectors have the form k times 1, 1. So they're just going to be multiples of the vector 1, 1 for k real but not equal to 0. And again, we can check to see that we've found our eigenvector appropriately by calculating c times 1, 1. And when we multiply this out, we get -1, -1. And so indeed, this is -1 times the vector 1, 1. So eigenvector of 1, 1 with eigenvalue -1. All right, last but not least, we're going to do this 3x3 example. We already know our eigenvalues. We found that they were 0, 3, and 5, and we want to find the eigenvectors corresponding to each of these eigenvalues. So I'm going to start by looking at lambda equals 0. I'm going to calculate a minus lambda I, so that's just a, and I'm going to solve AV equals 0. Okay, so all I'm going to do is row reduce A. So I have 3, 1, 2, 0, 3, 6, 0, 1, 2. And I'm just going to row reduce for a moment. I would recommend that you do the same thing. All right, so I landed at the following echelon form matrix. You probably went further and made this 1, 0, 0, but I wasn't paying attention. Okay, so if we have x, y, and z, then what does this tell me? It tells me that 3x is equal to 0, and that y plus 2z is equal to 0. So from my m and 0 equals 0. My first equation tells me x is 0. My second equation tells me that y equals -2z. And so my solutions are going to look like v equals 0, -2z, z. Okay. So my y was given, my y coordinate, my middle coordinate is given by -2 times my third coordinate. I can factor out a z if I like. I get 0, -2, 1 times z. Okay, so every eigenvector corresponding to lambda equals 0 has this form. If I just want one eigenvector from this set, I can choose z to be anything and choose that vector. All right, next lambda equals 3. I'm going to calculate a minus 3I, and then I will row reduce it to find solutions to a minus 3I times v equals 0. So my matrix that I'm going to be row reducing is going to be 0, 1, 2, 0, 0, 6, 0, 1, negative 1. All I've done is I've subtracted 3 from the diagonal. Okay, and now we're going to take just a minute and row reduce. Okay, so I end up with this reduced row echelon form, and if I write this out, I get that y equals 0 and z equals 0. And we can see that x is a free variable. It doesn't appear in any of these equations. So my solutions v are all going to have the form x, 0, 0. X can be anything. That is, this is just going to be a multiple of the vector 1, 0, 0. And we might have expected this because we can see from this original matrix A that the vector 1, 0, 0 maps to 3, 0, 0. All right, so we've got eigenvectors for 2 of our eigenvalues. We've got one left to do, lambda equals 5. Okay, when lambda equals 5, we're going to be solving a minus lambda I times v is equal to 0. So we're looking for all vectors v that make this true. Okay, so I'm going to start by calculating a minus 5i. That means I'm going to just be subtracting 5 from everything on the diagonal. Okay. So I end up with the matrix negative 2, 1, 2, 0, negative 2, 6, 0, 1, negative 3. And I'm going to row reduce this again. Okay, so this is as far as I went. You don't have to put it in reduced row echelon form. I would recommend that you clear out zeros above pivots as well as below them. Okay, so this tells me that negative 2x plus 5z equals 0 if these are columns x, y, and z. And it tells me that y minus 3z equals 0. 0, 0. Okay. So x is equal to 5 halves z. Y is equal to 3z. And z is just free. Okay. So my eigenvectors are going to have the form 5 halves z, 3z, z. For z in any real number, well, except 0. Okay, we can factor out our z. Okay. So all of our eigenvectors are going to have this form. This might be a little bit nicer looking if we rewrote this as 6, or whoops, we're going to just multiply every piece of this by 2. So I have 5, 6, 2. Okay, for k and r. Every eigenvector corresponding to lambda equals 5 is going to have this form. And you can always check it by calculating A times this vector 5, 6, 2. All right, we did it.